So my name is İpek Özkay. I'm a principal researcher at the Software Solutions Directorate, and I work predominantly at the architecture practices area. I'm going to be talking about improving software sustainability through a data-driven approach and with technical debt management. I don't know if there's anyone who has never heard the term technical debt. So I'll actually start by just getting to the chase and defining technical debt, because if you've heard technical debt, you also probably have heard of all different kinds of aspects of it. Well, it's my manager who hasn't made the right decision, that's technical debt. It's that skilled, unskilled worker that we put on the project that did not do the right thing is technical debt. Or we didn't document technical debt. Well, we think those are all areas of improvement that could inject technical debt to the system, but they're not really helpful. So we actually take a very software development artifact focus and quantitative focus to technical debt. So we define it as a software design issue that exists in the executable artifact of the system. This could be code, it could be automated test suites, which actually we see a lot of evidence there, or it could be build scripts. We also see a lot of evidence that technical debt as a design issue is traceable to many areas in the software. So this could be as a result of impact of change, to what extent you need to make the change throughout the system, or the change could be simple, but because of all the dependencies in the system, if you don't make that change, you might actually observe a lot of impact throughout. And last, there is a quantifiable effect of technical debt that is observable by the developers and the stakeholders. And this could be increased number of defects, increase of number of changes that need to happen, or areas of maintainability that it's creating. But all of these are symptoms of technical debt. By themselves, they are not technical debt. So we trace it initially to a focus area where violating particular architectural patterns or decisions or maintainability rules actually result in some of these ilks throughout the system. And let me give a couple examples that come from actually collaborators that we work with and we're currently working with that are real and dear to their hearts. The first one is they picked a model view controller framework initially for their system. This was a contractor working with a DoD organization, and this actually was a successful system at the end of the day. But they had to actually spend a lot of money afterwards to redo it. What they did is, because they were trying to do a demo of the system initially, they did not follow the model view framework pattern there, and they had to actually do a lot of retrofit afterwards. So if I were to bring this back, this is typical framework modifiability violation or pattern conformance issue. Some other typical examples, two modules that are very highly coupled that shouldn't have been in the first place. The developers knew the problem, but they just could not get ahead of the issue there. Or a very simple API call that created a lot of pain throughout the system. So with that, what we thought at the end is a timeline approach is actually the most helpful in terms of understanding what's happening, but most importantly to map both our research approach as well as the tooling out there to really get ahead of the problem. So there's a time that the technical debt is incurred. Initially, the contractor does something. Maybe they do inform the customer, or they may not. And then contractor does recognize that there's an issue, but does not declare this to the customer. And there's an optimal time where the contractors could still actually redo the system without additional costs, but that time typically passes as well. And these are generalizations from some of the typical examples we've observed. And by the time the government actually adopts the system, they don't know where the problem is. They don't know where to start to solve the problem. It's actually a big problem that they have to deal with. So our ideal vision, this is the first year of a second year project, is to make technical debt as a strategic software development approach rather than this mess that you adopt with. And here's another example. This is a real example, and the beauty of this example for me and my research team is that we actually had the pleasure of working both with the contractor and the customer side of the project, and that actually shows how there's an earlier point of time where this problem would not result in millions of dollars of added costs or lines of code that they needed to redo. And bottom line, we're trying to identify these indicators starting with the modifiability aspects. We'll move on to security this year. And what are the data sets that are actually essential? Because there are also examples where there are violations of some of these examples, but they do not necessarily end up in some of the added costs, and they do not necessarily have higher priority in the fixing. We have 3 research questions, and 3 questions actually that drive the work. What do our stakeholders really care about? And this comes from the technical debt became very popularized within the past 5 years, although as a terminology it's been around for a couple decades. And this was both driven by the agile software development movement, as well as the researchers starting to pay more attention to it, recognizing it actually brings both architecture and code violations and quality aspects, empirical research, as well as the tooling together. So we did work in terms of looking at what the stakeholders care about. Second is the rubber hits the road. Can we actually detect any of these issues that are really higher priority and can actually reduce the overall resources, especially during sustainability? And bottom line of this kind of work is data. What kind of data should organizations be collecting and what do we correlate with? So let me start with the stakeholders and what kind of issues would be benefited from technical debt management. So in order to understand this better, we stepped back and said, okay, we need to talk to people because there's a lover and haters aspect of technical debt. The haters are, well, it's just a metaphor. There's not necessarily much science and quantification to it. Yeah, we like expressing our problems as that, but leave it as that. So there's one camp of both researchers as well as practitioners. And there's another camp that actually, their eyes light up when we talk to them. It's like, yes, that's my problem. I cannot communicate to it. I can show you the evidence. This is how I work through it. But I cannot necessarily bring that to the higher priority and visibility for people to pay more attention to it. We were very fortunate. We worked with 4 organizations, and we designed a survey, and we signed NDAs with these organizations. We also went back and forth whether we should disseminate this survey openly or work with individual organizations. And we took the individual organization route. Although it took a lot of time to set it up, it actually is paying back really beautifully. We had a very high response rate. 1 industry organization, global, 1 government contractor, again with a global footprint, 1 sustainment organization, and 1 government lab. And the questions, is there a common understanding? Are issues that they're really dealing with architecturally in nature? Because some of our earlier work demonstrated that all of those symptoms that I talked about at the end of the day result in the root cause being some architectural issue that you may not have recognized or you've recognized but not articulated. And can we learn from best practices? Are these organizations actually are using things that we can disseminate to the others? So the first finding is technical debt is just not a cute metaphor. It actually has real footing. People do talk about it commonly, in developers and managers understand it. And the number 1 pain point actually did come out to be bad architecture choices. These charts are not very legible, but we have papers of the results that I'm happy to share with. And by putting that as their top choice, what they're saying is we don't know how to deal with it, we are not able to communicate it, and by the time we recognize it, actually becomes such a huge problem. The rest of the issues that were followed with actually has relationships to the architecture as well, like obsolete code, overly complex dependencies, not being able to update test suites when you refactor the system, and so on. And the second is a huge chunk of the respondents said this actually dealing with the consequences created a lot of painful resources, and yet the management practices that they have or the technical practices they have are more anecdotal, they are more qualitative and not necessarily there to be able to help them. And the dominant practice that they used was maybe putting it in the backlog or through retrospectives or communication. And the most interesting one to us is tools do not capture it, tools are not helping. The number 1 tool that developers said they were using were issue trackers, but even that was typically not a very good practice. So the significance, although this research has been around for 5 years, this is the first of its kind of this evidence that's brought to the table. It actually focuses the tooling aspect on the architecture of the system and how can you bring that detection to a more usable area. And it's also helping us get engaged with some of these organizations further, where we're doing artifact analysis, training, and collecting more data. And we have the publication if anybody's interested. Next, can we detect these indicators of design issues that we call indicators, and which one of those result in technical debt? So the detection actually has several aspects of it. That the timeline as one of our outcomes is really helping both us and our stakeholders communicate this better. So at what time do you detect? Ideally, you detect it at the time that you are making that trade-off, or when you start seeing the symptoms. And what is the data set that you need to correlate with? We did say that there's early as well as later indicators, like the increasing number of defects, change proneness, and whatnot. So there's that data set that needs to be there. But today, the development environments actually do provide capabilities for those kinds of data sets to be stored. And how do you make that understandable to a manager or a PM who might need to make prioritization decisions based on that? So the first step was we did a tooling analysis. There are quite a number of commercial tools out there that claim to do this kind of analysis. Most of them tend to be more static analysis tools. There are also emerging research tools. So we did a experimentation in terms of, well, there are some basic things that we would like to understand. For example, coupling, or API misusage, or being able to define rules such as this particular class should not be talking to that class, and if that happens, then it should be flagged. And as a result, we selected an environment called SonarQube. You might have heard of this. This is an open source environment. It has a plugin development environment where you can build your own plugins on top of it. And the reason we selected this was opportunistic, because once we package our own detection as well as reusing existing ones, because some of our collaborators already are using it, they said they would be happy to provide us more data. So the cons of this, though, because technical debt has become almost like a consulting selling point, they do exist some existing measurement ways. A lot of people don't use them because they create a false fear factor. For example, the result might be you have $8 million of technical debt, whereas the project might in the first place cost $1 million. So that mismatch actually is not validated. So although it's a con from the perspective of the existing environment, it's actually also working to our benefit in terms of the comparisons. So we did some initial analysis with some of the existing data and software we have. And in a sample project, this is called Connect. It's an health IT exchange for government that we had done an architecture evaluation of a couple years ago. We're already also continued to be in communication with the development team. And because it's open source, all of the code, all of the development environment, the issues and whatnot is open source. So this particular project went through several major refactorings, and looking at different time frames of the project, as well as the modularity and modifiability issues that we look at, we found that the major modifiability issues make up about the 16% of the overall system. Yet that 16% of the system accounts for a big chunk of the existing bugs, 84% before a major refactoring, but even after the major refactoring, 47%. So this gives us confidence that we're on the right path, and we're continuing on collecting more of these, doing the experimentation and collecting further of the data. The significance is, so the initial detection with the code starts with the code quality aspects, like coupling or dependency violations, or some of the things like God class. They are code quality aspects. By looking at across the system, we are bringing an architectural perspective to it, and we're also starting to build a validation environment. And earlier, Kevin said that we work with external organizations significantly. One of our team members have been working with Drexel University and testing some of these, and those publications are also available for further details. And last, the data needs. This is actually the hardest part of this project, because collecting the right data and enforcing that data collection to organizations has been humbling. but we've been fortunate because of our collaborators and their willingness to actually work with us. So if we look at what are the data needs, and that's also the #1 question that we get asked, if we want to get ahead of this, what should we actually be looking at? What kind of data should we be collecting? So if we look at some of the independent examples that come from the developers as well as the systems we looked at, for example, replicated functionality comes up across as unintentional issues that accumulate in technical debt, or functionality depending on an in-house algorithm that was not developed to par that might have to change. So the analysis inputs then becomes like code clones, dependencies, and so those are the things that we would look into detection. The bottom line in terms of the independent output that you look at is becomes money. Did I spend added time because those issues were there in adding new functionality? Were there more defects in that area? Was I tracking those kinds of things? So while we can find the independent examples and analysis outputs, the dependent variables always are based on the competency of the organization. But we have 2 test beds that we're already working with, and as I said, we're also looking into the future-looking ones with our collaborators. One is an internal communication terminal. This is an embedded kind of system, so we also look at both aspects, although the methods that go into their development are different. And there's a lot of qualitative information in terms of the tribal knowledge, in terms of major refactorings over program lifetime, a lot of slide presentations, but we also have data in terms of some of their change proneness and defect proneness with some versions, as well as some actually files they kept, where they kept an Excel sheet of technical debt that they were accumulating. So that's and we have the internal SCI history, about 5 years. The goal through this is to use these test beds and then to generalize and put it out there as examples where others can build on. And the other one is the Connect one that I mentioned. It's a government source for the Health IT Exchange, and we have similar data, especially the commits and the GEA database and the code repository. So to give you a kind of overview of the kind of visualization we're looking at, so this is from Connect. What you would get out of this is if you look at multiple versions of it, which one actually has the most accumulated magnitude of most of the issues. So this is, in this case, it's the version 3.3. This happens to be the one that we did the architecture evaluation, which is a scenario-based approach, but they also did the refactoring and that they're sharing their insights with us. And then if you dig deeper, what are some of the areas, like for example, if you were using frameworks that go back to the API violations, how do they culminate, and can I dig deeper? And if I get another step down in the interactive way of looking into it, what are some of the violations that I might actually look at? This is for feedback to the developer, whereas these kinds of visualizations might be feedback to the actual manager. And looking forward, this is we're starting the 2nd year. Our goal at the end of this year is to be able to put out our extensible framework, to be able to have other researchers build onto it, as well as do more tests. The relationship of testing and technical debt come extensively in our initial work, as well as a lot of the collaborator examples. So that's an area that we do hope to look further into as future work and extensions to the data sets. We do have a 1-day course that we're piloting, and our publications as well if there are anybody interested in further details. And a large team, and also a lot of external collaborators to protect the innocent. I cannot declare who the collaborators were, but they themselves would probably do. But we're very fortunate and thankful to them.